Alright, these are going to be the rules that we went over in class for how to draw molecular compounds. Our first step is to total up the number of electrons in the compound that we're going to draw. So we have two compounds here that we're going to work with for practice. The first one, CH4, this is methane. And our second one is going to be CCl4, which is carbon tetrachloride. Now, how do we know how many valence electrons there are? Well, the number of valence electrons is based on the location in the periodic table. We discussed this in a previous chapter. Our alkali metals all have 1, alkaline earth metals 2, skip over here, 3, 4, 5, 6, 7, and 8. Helium is an exception because remember that hydrogen and helium are in the first row of the periodic table, which means that hydrogen is basically 1s1 and helium 1s2, and 1s2, that's basically a full outer shell because it only has the first level. There is no p, remember, on the first in the first level in our drawings. Alright, so we're going to total up the number of electrons in our two compounds for practice. Remember that we're talking about covalent compounds here, so if you're wondering why I didn't say anything about the transition metals, and technically all of these things, because those form ionic compounds, a metal and a non-metal. So usually we're going to be dealing with hydrogen sometimes, beryllium, and then pretty much this section of the periodic table. So this is why I didn't tell you how many valence electrons these have. Alright, so let's total up the number of electrons. So first we're going to find carbon. Carbon is right over here, and it has 4 valence electrons. So 4. Hydrogen, right here, has 1 valence electron, and there are 4 of them, so we're going to multiply that by 4, and so our total number of electrons in our hydrogen is 4. Add this together, the total number of electrons we need to place for methane is going to be 8. Alright, let's practice it again for our second compound, carbon tetrachloride. So we just said that carbon has 4. Let's locate chlorine. Here it is. It has 7. And there are 4 of them, so 7 times 4, there's going to be 28 electrons. Add this together, we need to place a total of 32 electrons in this compound. Alright, our next step, we're going to place our first element in the center. Now when we get to more complex ones, this may not always work, but for the purposes of the ones that we're going to be working with in class, at least for right now, this should work. So we're going to place our carbon in the center, and we're going to connect everything else to it. And so here we go. Alright, so we've connected everything to our carbon. Now remember that a line represents a bond, and that a bond represents one shared pair of electrons, in other words 2 electrons. So we're now going to subtract the electrons that we have placed so far in this compound. So this is going to be 2 electrons, 4, 6, 8. We have placed 8 electrons. So if we go back to our methane, we had 8 to place. We've placed 8, and we have no electrons left over. Alright, and we'll go back to this in a minute, but let's now take a look at our second one, which was carbon tetrachloride. So we're going to do the same thing. We're going to place our chlorines around our carbon. Alright, and again we have placed 2, 4, 6, 8 electrons. In this case we started with 32. We're going to subtract the 8 that we have already placed in our drawing, and that gives us a leftover of 24 electrons that we still need to place. Alright, so we're going to do a check now and see which elements are deficient in electrons. In other words, do we have elements in our drawing that don't have enough electrons to have a full outer shell? Because that is our goal. We want all of our elements to have a full outer shell by sharing electrons or by holding on to their own electrons. So we know that carbon wants 8, And our carbon has 8. 2, 4, 6, 8. We drew those, so our carbon is happy. Hydrogen doesn't want 8. Remember, hydrogen only wants 2. Keep that in mind. You just need to memorize it, that hydrogen, again, being in the first row of the periodic table, it's 1s1 normally. If it now is 1s2, it's full. So each of our hydrogens has 2 electrons. So this works out. Everyone has the number of electrons they want. We don't have any electrons left over, and so we're finished. This would be the final drawing for methane. Now let's look at our second one, carbon tetrachloride. Our carbon has 8, 2, 4, 6, 8, but each of our chlorines right now only have 2, right? This chlorine has only 2 electrons. All right, so what we're going to do, we have a bunch of electrons here we can place 24 more. We're going to start giving each of our chlorines a full outer shell of 8. So any dots that we draw, these are going to be electrons that are not shared. These are going to be unshared electrons. The dash represented shared electrons that are sort of counting both for the chlorine and for the carbon. All right, so let's start with this one. 1, 2, 3, 4, 5, 6. This one would now have 8, right? 2, 4, 6, and these two make 8. So we've now placed six of our electrons. So we could take away 6, and that gives us 18. And I'm just going to go ahead and continue with this. We know that each of these would need 6 more dots, so let's do that. So we need to place 18. 1, 2, 3, 4, 5, 6. That one now has 8. 7, 8, 9, 10, 11, 12. Now that one has 8. 13, 14, 15, 16, 17, 18. So we have now placed all of our electrons, and if we double check, this chlorine has 8, this one has 8, this one has 8, and this one has 8, and our carbon we said had 8, and so everybody is got a full outer shell. They're all happy. We don't have any electrons left over, and so we're finished. So this would be the final drawing for carbon tetrachloride. Alright, so it would be nice if they all worked out nice and pretty, but they don't. So let's take a look at this one, carbon dioxide, and this one's going to have, we're going to run into a problem. So we're going to start with our original rules. Oxygen has 6 valence electrons, so there's 2 of them, so that makes 12. Carbon has 4, so we're going to add those together. That gives us a total of 16 electrons we're going to place. That was our first step. Step 2, we're going to put our carbon in the middle, and we're going to attach our oxygens to it. Alright, and we're going to subtract for the electrons that we've currently placed, so that's 2, and this second dash makes 4, so 16 minus 4, we now have to place 12 more. Alright, I can see that my oxygens, I'm going to start with oxygens, my oxygens right now only have 2, we know they want 8, so I'm going to go ahead and start with that. So 1, 2, 3, 4, 5, 6, that one's good. I'm going to come back to the other side, 7, 8, 9, 10, 11, 12, and now that one's good, and it kind of looks like we're done, but take a look at our carbon, it does not have 8, it actually only has 4. Alright, so here is what we're going to do if we run out of electrons. We have placed all 12. We don't have any more electrons to place, so you can't just start putting dots. There aren't any more. What we can do is we can have the oxygen share another pair. So oxygen's generous. It has 8. It says, hey, carbon, you don't have enough. Here's what we're going to do. We're going to share one of our pairs with you. So we draw a second line here. This is called a double bond. Now the oxygen still has 8. 1, 2, 3, 4, 5, 6, 7, 8. But because this pair is now shared with the carbon, our carbon now has 6. It's up to 6, right? 2, 4, 6. So we can do the same thing with the other oxygen. Come over here, do that, and now make a double bond on this side. This oxygen still has 8 because it just changed a pair from being its own to being shared. And our carbon now has 1, 2, 3, 4 of these, so 2, 4, 6, 8. Our oxygen still have 8, and so this is what carbon dioxide would look like, CO2. Everybody now has 8, and these would disappear, this and this. And so this is what this one would look like. All right, let's try that again. Here's another one where you're going to see a similar problem. We're going to do nitrogen N2. And while we're on the subject, just a little reminder that certain elements are always found as diatomic molecules in nature. Nitrogen is one of them. And I had taught my class, one way to remember this would be Brinkelhoff. Brinklhof. These are all the ones that are found as diatomics: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So if you were talking about iodine, let's just say by itself in nature, it would be found as I2. Oxygen floating around in our atmosphere, it's found as O2. And nitrogen, which is the one we're going to draw, is found as N2. All right, so nitrogen has 5. There's 2 of them. We're going to be placing 10 electrons. So, first step, connect our nitrogens, take away 2 electrons. We now have to place 8 more. So I'm going to make this symmetrical. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Now, each of our nitrogens has, 2, 4, 6. They each only have 6 electrons. So what I'm going to do is I'm going to take a pair, and I'm going to take this pair away, and I'm going to share it with the other one. Now, this one, 2, 4, 6, it still has 6. The other one has 2, 4, 6, it now has 8. So we still haven't really solved our problem. So what we can do is do the same thing again. We'll take 2 of the electrons off of our other nitrogen, right here. We'll take these 2, and we'll share them also. And add another one right here. And now, each of them will have 8. We'll have 2, 4, 6, and the 2 dots make 8 for this one. And then our 2, 4, 6, and our 2 dots, and that will solve this one. And now both of our nitrogens have 8. So this works out. We can see a similar issue if we do it with oxygen. Let's do oxygen. So oxygen is O2. I'm going to run out of space, but each oxygen has 6, so we're placing a total of 12. If we start by connecting them, we've made 1 bond, take away 2. Now we have 10 electrons to place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, we've got a problem. The one on the right has 8, but the one on the left only has 6. So again, the one on the right can be generous. Take away 2, and instead of hogging them, he'll share them. This one still has 8, and now our one on the left, 1, 2, 3, 4, 5, 6, 7, 8. This one has 8, this one has 8, and we've drawn our oxygen. So try to follow all the rules, but if we run into problem number 1, you run out of electrons, you've placed all the dots you have, and everybody doesn't have 8, then start sharing, and you can get to everybody sharing 8. A quick comment on this that I wanted to mention: not every element can form double bonds or triple bonds. Hydrogen will never do it. Remember, hydrogen only wants 2. Don't try to make double bonds to hydrogen. Nitrogen, oxygen, and carbon are common ones that you'll see double bonds or triple bonds. And you don't ever see anything beyond a triple bond. You would never see like a quadruple bond. So keep that in mind. One other comment on this: there are actually a couple of exceptions, 2 notable exceptions to this rule, that are beryllium and boron. it turns out that these two will be electron deficient. You will not get 8 around them, and it's okay. Beryllium is an exception. If you have BeH2, you would actually end up with this. Don't try to make double bonds. It's okay that beryllium only made 2 bonds, that it only has 4 electrons. It's because of its location on the periodic table, and when we draw 3-dimensional structures for this, you'll see why it fits this way. So beryllium, you just have to memorize it. It will be electron deficient, and it's okay. And you're going to see the same thing with boron, whereas beryllium will make 2 bonds, boron will typically make 3. So for example, you might see BH3, and it ends up looking like this, H, H, H. You only end up here with, as you can see, it's surrounded only by 6 electrons and not 8, but again, it's okay. So these are 2 that you just have to memorize. Beryllium will be electron deficient. It will typically only make 2 bonds. Boron will be electron deficient. It will typically only make 3 bonds. Don't try to make double bonds. These are okay to be left alone. Alright, so here's another weird issue. Let's say that you give every element 8 electrons, and now you still have electrons to place and you don't know where to put them. You have too many electrons. So look at this one. This is an iodide ion. Now when it's an ion, what you're going to do is you're going to total up the electrons. Iodine has 7, so you multiply that. There's 3 iodines, so there's going to be a total of 21 electrons. And you're going to add in, since this has a -1 charge, that means it has an extra electron. And so we actually are placing a total of 22 electrons. So if we connect our iodines, we're just going to put an iodine in the middle and put the other 2 connected to it. What we see here is we have now placed 4 electrons. If we take away 4, we now have 18 more electrons to place. So I'm just going to start putting them around. I'll start on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now at this point, I have now placed 16 electrons, and everybody's got 8. If we look at this, you will see we have 2, 4, 6, 8 on this one, 2, 4, 6, 8 on this one, and 2, 4, 6, 8 on this one. Everybody's got 8, and yet we still have 2 electrons left over. So it's going to look weird, but you are actually going to put them on the element in the middle. That is what you do. You actually stick them on the element in the middle. And you will see this happen occasionally. Remember, try to follow the rules. The only time this can happen, they have to be low enough on the periodic table that they have extra space. What actually happens on a, I don't want to get into it too much, but basically if they're low enough on the periodic table, they could throw those extra electrons into an empty d orbital. So they have extra space. So things that are high on the table, like fluorine, for example, it doesn't have, it actually, fluorine is 1s2, 2s2, 2p5. There is no d on level 2, so there would be nowhere for it to throw extra electrons. Iodine, on the other hand, is much further down. It's actually 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then it continues, 4p6, and then 5s2, 4d10, 5p5. Now, this is actually iodine. I know this is you don't want to go back to this chapter, but the bottom line is, technically, on level 5, there is a 5d. It hasn't been filled yet. So if iodine was to have an extra pair of electrons stuck on it, it would have a place to put them. It could actually put them in 5d. So that is why only some elements can do this. probably more information than you wanted to know, but that is why it can happen. And we're going to see something kind of weird also with this one over here. This is phosphorus pentachloride. So when we do this one, oh actually, and I wanted to go back to this for a second. Now that we've drawn the iodine, since it has a negative charge, you actually put brackets around it and you put the negative here, showing it has a negative charge. I'll show you another example of one with a charge in a minute. Alright, so PCl5, phosphorus pentachloride. If we add all of this up, we have 7 times 5 is 35 for the chlorine, plus our phosphorus has 5, I believe, and so that gives us a total of 40 electrons. Alright, so remember what I told you, we're going to put our element in the middle, our first one, and we're going to surround it with the others. Now, notice you have 5 chlorines. You are actually going to do this. You're going to do 1, 2, 3, 4, 5. That looks strange. You now have our phosphorus with 10 electrons around it rather than 8, but phosphorus is one of these, and it will be an exception to the rule. So if you see something like this, an element and more than 4 things around it, you can just go ahead and connect them to the middle one, and we'll go from there. So we've gone ahead and we've connected the chlorines. Those are 5 bonds. That makes 10 electrons we've placed. We need to place 30 more electrons. So let's start making dots around our chlorines. And we know each one's going to need 6 more dots, so let's see if that works. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. That takes care of all 30 electrons. All of our chlorines have 8, and even though our phosphorus has too many, this is the correct drawing. And so this is basically how you're going to handle leftover electrons. If you've given everybody 8 and you basically have already shared everything, do what you did with the iodine here and just put the dots on the one in the middle. And if you have an element and let's say 5 around it, PCl5, then in a case like this, go ahead and surround it with all 5. And even though our phosphorus is breaking the rule, it is low enough on the periodic table that it can do that. And so that is basically how you're going to do those. Okay, so you remember our polyatomics from the last chapter, and you had to memorize some of them. So when you're doing those, and I mentioned this on the previous slide, for example, let's say you're going to draw ammonium. Ammonium was NH4 with a plus. In other words, when we're totaling up our electrons, nitrogen has 5. There's 4 hydrogens, and each of them have 1, and that gives us 9. But now we see that it has a positive charge, which means it's missing an electron, so we go ahead and take 1 away, and so actually ammonium only has 8. Now when we draw it, we follow our rules. We're going to connect our hydrogens to the nitrogen. 1, 2, 3, 4. And guess what? In this case, this is 2, 4, 6, 8. That gives our nitrogen 8. Each of our hydrogens have 2, which is all they want. And then we're going to put brackets around this to show that it has a positive charge. We can also do this with, let's try another one. Let's do carbonate. So carbonate is CO3 with a negative 2 charge. So when we total up our electrons, we're going to have 4 for our carbon. Each oxygen has 6, and there's 3 of them, so that's another 18. And we're going to add to that the 2 for our extra 2 electrons. So that gives us a total of 24 electrons to place. So here we go. So we're going to do our carbon, our oxygen, and our other oxygen. That is going to get rid of 6. We need to place 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Looks like we're done, but actually we're not, because our carbon only has 6 electrons around it. So remember, what was our other rule if we run out of electrons? Well, we'll just take a pair off of one of our oxygens, and we will make a double bond here. Now you might say, how do you know which oxygen? Let's go ahead and put our brackets, and this would have, get this out of the way, this would have a -2 charge. Alright, so you might say, how do we know where to put the double bond? Because technically it looks like there's 3 different ways we could draw this. We could put it in 3 different places. And there's actually a name for this. This is called resonance. And you're going to see this sometimes. What happens with resonance is that there's more than one way to draw it. Basically, there's more than one place you could put this double bond and get the same exact drawing. And what we know really happens in resonance is that it doesn't just flip around and go from one oxygen to another, but there's sort of a partial, sort of a shared partial bond between all 3 of the oxygens. However, the way we often draw resonance is like I put it on our title screen. Let me pull that up again. Alright, so I stuck another one here just to show you. This would be NO3. If you remember our polyatomics, NO3 negative. This would actually be nitrate. And nitrate's another example, and this is how it's often drawn. They show the arrows showing sort of the 3 ways that it can be drawn. See the double bond? Notice it is in 3 different places, here, here, and here. In reality, none of those really exist, and we'll talk more about that in class. But this is a way that you could represent it, and this is the name for it. It's called resonance, and what you want to do when you're drawing it is actually what you usually would do is draw all the possibilities. Alright, so let's look at some practice ones that may or may not follow the rules. So let's see where we're at. So this is sulfur hexafluoride. And I think you can already see there's going to be a rule broken here. If we follow our rule of putting our sulfur in the middle and surrounding it with the fluorines, there's going to be 6 fluorines around that sulfur. And that's okay. Sulfur can break that rule. So sulfur has 6 electrons, and each fluorine has 7, so that's going to be another 42. And so that's going to be a total of 48 electrons. So we'll start by surrounding our sulfur with fluorines, which looks pretty weird, but this is what happens. Again, when we draw 3D models of these, or when we actually put together 3D models of these, I think it'll be more clear of what these look like and how this can happen in 3-dimensional space. Alright, so 2, 4, 6, 8, 10, 12. We've used up 12. And so we still need to place 36 electrons. So let's start putting them around the fluorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. We've placed all 36, and all of our fluorines have 8. If there were still 2 more left over, what would we do with them? We would stick them on the sulfur like that. However, we don't need to do that because we've used all of our electrons. Alright, let's look at our next one. Beryllium dichloride. Alright, so beryllium has 2 electrons. Chlorine has 7. There's 2 of them. That's 14. We're going to place 16. We put our beryllium in the middle. Put our chlorines on the side. That's 4 that we've placed so far. Alright, so we need to place 12 more. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've placed all of our electrons. We don't have any left over. Now it looks like our beryllium is going to need double bonds, but remember that beryllium is an exception, and it's okay that it only made 2 bonds here. It's not going to get double bonds, so be very careful with that. If this was something other than beryllium, like carbon or something like that, then yes, you can't leave it alone. All right, and let's look at our last one. So this is nitrite, the polyatomic. So let's add up our electrons. There's 5 for nitrogen. Each oxygen has 6, so that's another 12. And it has a -1 charge, so we're going to add another one there. That gives us a total of 18 electrons. We're going to put our nitrogen in the middle, put our oxygens over here. That takes care of 4. So that's 14 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I've placed all of my electrons. Our oxygens have 8, but our nitrogen only has 6. What does that mean? That means that we are going to need to share. Which oxygen are we going to use for sharing? Well, this is that special example. We called it resonance. I'm just going to share from this side, but that means that in reality, you could draw it either way, and the proper thing to do would actually be to draw it both ways. So you would draw this like that with its negative charge, and then you'd put an arrow showing that it could also be drawn this way. Remember, which way is it really in nature? Neither. It's actually something in between, and that would be our drawing. And so this would be an example of resonance. All right, and you really don't need to know this part right now, but I figured I'd add it. There were a couple of practice problems on the worksheet where they looked a little more complicated like this. So what you're going to do in a case like this, notice that it's not just one carbon, but each of these have 2 carbons. And what I suggest to do in a case like these, or in cases like these, would be to try to make them symmetrical. You can't connect hydrogens to each other. In other words, you can't do this, because remember, hydrogen can only have 2 electrons around it, and if you do this, each hydrogen's going to have 4. So we know that the hydrogens have to be on the end. They can't be something that's in the middle of a compound. They have to be terminal, so to speak. All right, so let's total up our electrons on all 3 of these, and let's see what we've got. So our first one, each carbon has 4, so that's 8, and each hydrogen has 1, and there's 6 of those. So this one's going to have 14. Our second one, again, our carbon, that's 8. In this case, 4. So that's 12. And this one, our carbon has 8, but only 2 hydrogens. That's 10. Okay. So what we're going to do is we're going to put our carbons in the middle. And let's go ahead and connect our hydrogens. We're going to make it symmetrical. We can put 3 on each of our carbons, and we'll see where we're at. Alright, so our hydrogens only want 2, and our hydrogens all have 2. And our carbons, they each want 8, which would be 4 bonds, and currently it looks like they all have that. Let's just double check that we've used all of our electrons. So this would be 2, 4, 6, 8, 10, 12, 14. We've used all of our electrons, and so this would be the correct drawing for, this is actually ethane. Alright, let's try our second one. So same thing, we have 12 electrons. We're going to start with our carbons, and let's make it symmetrical. So I'm going to draw my hydrogens kind of pretty like this. You don't have to. Alright, we've connected everything. This time we have 2, 4, 6, 8, 10, it looks like. We've taken care of 10 of our electrons, and we only have 2 left. Well, if I put the 2 on this carbon, the other carbon's going to be short. And if I put the 2 on this carbon, then again, the carbon on the right is going to be short. So the best way to solve this would be to let them share that pair of electrons. There we go. And now we've basically used all of our electrons. Our carbons have 8 and our hydrogens have 2, so we're happy. Let's look at our third example. I think you kind of see what's going to happen here. So again, we're going to connect our carbons, and here's our hydrogens off to the side. And this time we've placed 6. We have 4 more electrons to place. Well, we could do this and give each of our carbons 2, but if we do that, each of our carbons now only has 6. So if I go ahead and use my little rule here that maybe if this guy shares 2 of his with this carbon, the carbon on the right now has 8, but the carbon on the left still only has 6. So let's do this and share again. And now each of our carbons has 8. So in cases like these, this is ethine, this one's called ethene, and this one is ethane. But you can see here that we have single bonds, double bonds, and triple bonds. And obviously compounds can get a lot more complicated. Carbon can actually form rings, and we can see all kinds of things, but for the purposes of our class, hopefully this helps you with the drawing of simple compounds.